Okay, so again, I'm Sue Lessica. I'll be talking next about an IRP-RC-1 for advanced materials. So again, I'll start with some context talking about the sponsoring program, and that's the Advanced Reactor Technologies program. So the mission here is to identify and resolve technical challenges to enable the transition from our light water reactor fleet to our non-light water reactor technologies to gain the efficiencies and cost effectiveness that can go with a non-light water reactor fleet. And so here's our slide with the mission and objectives and how we're working with that. And as you can see on the objectives, many of those have to do with other areas, but in particular with the materials research program, including reducing technical barriers for deployment, increasing the affordability and the safety and sustainability, collaborating with industry, and developing the technical expertise and capabilities. So the Advanced Reactor Program includes an advanced materials R&D activities. And a lot of these new reactors require new materials or materials that have been used, current materials that are going to be used in a different way than they've been used before. And so here's some examples of reactors that really are of interest and are being developed by industry with support from the department, and that's the sodium fast reactor, a high temperature reactor, and molten salt reactor. So now let's delve into the scope of the IRP, and that's to develop fabrication technologies for compact heat exchangers. And so why is this of interest? Compact heat exchangers offer the potential for significant improvement in efficiencies and cost reduction for advanced reactor systems. And because compact heat exchangers can be used with several different types of coolants, many of which the advanced reactor designs are looking to utilize. They can also be used for supercritical CO2, for advanced energy conversion systems. So the versatility of compact heat exchangers is really making them of interest, and that's why it's the focus of one of the focuses of this IRP. Here we have some graphics showing how microchannel heat exchangers are fabricated. So there's photochemical etching of the plates. Those plates are then stacked. So this gives you the side view of on the cold flow side, and here are the connections for the flow. So that gives you an idea of how the heat exchanger functions. So there are several technical issues that have been identified. While it is true that compact heat exchangers have been fabricated using diffusion bonding, for the petrochemical industry, they're using much lower temperatures. They're using 316L. However, they have had success in that area. And so now the challenge is using higher temperature materials so that we can use these compact heat exchangers at the high temperatures that we're looking at our advanced reactors performing in. And so that's where the challenges come in, looking to operate at 750 C and above. And so the alloys that we're looking at are 800H and alloy 617. And our experience with these alloys using diffusion bonding is that there are challenges with creep and cyclic properties, particularly at the bond lines. That it's been shown to have limited ductility. And so that's where the challenge lies, because these properties are vital to the operation of the heat exchanger. We also are challenged in that we don't have current acceptance criteria that focus in on the right properties, so that we know and have confidence that the compact heat exchanger will perform as designed for as long as we expect. And so that's what we need to understand, have better diffusion bonding capabilities, and also acceptance criteria, so that we have confidence in the properties of the compact heat exchanger. Back in FY 2017, we funded an IRP project to advance towards ASME code case for compact heat exchangers. And so here are some of the results from that project that directly led to the development of this IRP. So here we have stress strain curves in a tension test at room temperature for 800H and some photographs of the failure. And in comparison, we have the same information for tension tests at 760 for the same alloys. And you can see the difference there of the failure methods and the debonding at the bond lines. And so this is what identified that this is an issue for us that needs further understanding and development. So proposals are sought for this IRP that will determine the scientific basis for the process property relationships for successful diffusion bonding of high temperature alloys that have been qualified or are being qualified for nuclear construction in Section 3, Division 5 of the ASME Boiler and Pressure Vessel Code. So this is the 800H or 617 that we've discussed. Okay, I'm sorry about that. So the goals of the IRP is to have improved mechanical behavior of the diffusion bonded materials and to approach the wrought values as closely as we can. So these would be improvements in creep, fatigue, and creep fatigue properties. We also want to have a predictive capability so that we can match the fabrication methods, fabrication parameters to the mechanical properties. And the next thing is to have develop acceptance criteria so that we can know and have confidence in the diffusion bonding process that was used to fabricate the compact heat exchanger. And those acceptance criteria would need to be then incorporated in nuclear codes and standards. And of course, that acceptance criteria will need to be validated under creep and cyclic loading environments. Let's see. So this call, as I discussed, is a direct follow-up of our prior IRP and an issue that was raised during that IRP. So it very well syncs in with our current advanced reactor program and is a very vital recognized need that we're trying to address here. And the topic was chosen because of the strength of the university community in understanding structure and property relationships, in using advanced characterization methods, and developing, joining processes and modeling. And so that we thought that this topic was well suited for university work. That being said, that there is a lot of expertise that the universities could pull in from both industry and the national labs to supplement the expertise that's already at the universities. And there's a lot of expertise also at the existing compact heat exchangers manufacturers. As I said, this technology has been used at lower temperatures, and pulling in some of that expertise may be a benefit as well. Here's the contact information for myself and Sam Sham, who's at Idaho National Laboratory. He's the technical POC for this area. And oh, there we go. So that's the end of my presentation. So let me check if Sam, are you on the line?
Yes, I am.
Great.
Okay. Thanks, Sam, for being here. We will take questions over the next few minutes. Please submit those to the question and answer box on the GoToWebinar application. We'll start with this question, Sue and Sam. For IRP-RC-1, is this only focused on conventional diffusion bonded materials or open for new technologies for diffusion bonding, which are possibly better?
Why don't you take that one, Sam?
Yes, I'm not quite sure in terms of the question in terms of materials. The materials that we're interested in are those that have been qualified for nuclear application, as well as some that are ongoing qualification process like alloy 709. But in terms of the diffusion bonding processes, that yes, any sort of a new methodologies that can effectively help us to solve this problem, of course, that will be within the scope. On the other hand, that any sort of new processes that we will need to see that there is a possibility of industrial scale up. So that, well, we would not require the IRP project team to do industrial scale up, but we would like to see some indication whereby that the process is not just limited to bench top. There is a route towards industrial scale up.
Does the application require both experimental and computational activities?
I would say so, because that one of the goals is to be able to come up with some predictive sort of methodology together with understanding of the properties and microstructure relationship in order for someone to be able to reduce the cycle of trying one set of diffusion bonding parameters and do the testing and then go back to this iterative process. So we really would like to see that there's some ModSim type of tools to be developed by these projects in order to augment the current sort of a state-of-the-art process practiced by the industry. Over.
Similar question, but a little bit different flavor. Are you interested in developing a code case for compact heat exchangers?
The code case, first of all, that's probably that we are interested for this call to develop the code case for the acceptance criteria. Current acceptance criteria in the ASME code is to just sort of do this process qualification. You diffusion bond a stack of metal sheets, maybe 50 or 100, I forgot the numbers, and then you make samples to do tensile test. And what we found out was that those tests are not discriminate enough to rule out some of those of bond line failures that the Sue showed in some of those pictures. So we're looking for looking for a good acceptance criteria, be in the form of either looking at microstructure or look at some mechanical property testing, so that if a process, diffusion process, that diffusion bonding process that pass those acceptance criteria, that we have a confidence that those type of bond line failures under creep or creep fatigue condition will not occur. So that will be something that we're looking for as stated in the goal. Over.
Would it be possible to use new materials that have not been approved by ASME at the moment?
Well, that is sort of difficult. As you see that if you pick some material that it works, like we saw that 316L grade works very well, but that's once that we switch to similar chemistry, a little bit difference going to the 316H grade. The vendors had a lot of issues in terms of doing diffusion bonding process. So I think that the low-hanging fruit is that we would like the project team to help us to sort of diffusion bonding, something that we can use in nuclear applications. And then these mod sim tools that we would like to see developed as part of the goal is so that we can use that type of techniques and that type of understanding to be able to sort of do diffusion bonding for some future alloys. Over.
Right. So just to add to Sam's answer, yeah, we're looking to use this technology in the short term, and that means using alloys that are already have been accepted in the code case, and so that's why we made that the focus here.
Do you foresee any need for thermal hydraulic studies associated with this IRP?
Only to the extent that thermal hydraulics will help us to understand the diffusion bonding process, but sort of not being a thermal hydraulic person, I will say that that does not seems to be something that helps, but I don't know in terms of the type of a thermal hydraulic analysis that the questioner has in mind. Over.
Are there any other bonding techniques that are welcomed apart from diffusion bonding?
Well, for sort of sticking two pieces of materials together, probably that sort of diffusion bonding will be sort of what I would gather to be the process. But how you do the diffusion bonding, whether you heat it or use some sort of a spark plasma sintering, there are a lot of different sort of techniques to press two similar materials together to form a sort of a single material. So whether or not that the current process that a commercial vendor uses to diffusion bond for all these layers or sheets of metals together, we're open to innovation in that. Over.
Would you be interested in using non-destructive evaluation methods as part of developing the ASME code case acceptance criteria?
Definitely, that we're open to that if it can do the job, and it also that if it's not too burdensome. For example, that when we look at acceptance criteria that involve testing for half a year, so those are not really suitable acceptance criteria for the advanced reactor developers or vendors to buy a compact heat exchanger. So we have sort of strike the balance, but obviously that is a good thought in terms of any NDE type of methodology. Over.
Is environmental testing of mechanical properties in advanced reactor coolants of interest?
That is a little bit different than the intent of this call. So therefore, obviously that when you use a compact heat exchanger for any advanced reactor applications, coolant will get into the picture. But obviously that is the part that we rely on designers to select sort of the right materials, or that there are sort of other controls in terms of chemistry controls that make it work. So the focus of this IRP is to make this a compact heat exchanger. So it's not that coolant effect is not important, but it's not this focus. Over.
Is the
To add
functionally...
on to what Sam,
Go ahead, Sue.
I'm sorry. To add on to what Sam said, our goal with the IRP is to make the results of it as applicable to as many reactor types as possible, and so that's why we're not focusing it on any particular reactor type.
Is the functionally graded material fabricated by additive manufacturing of interest in this IRP?
This is a tough question, because after all that we want to sort of support a near-term deployment. So therefore that those processes that I don't believe that it is sort of adopted by either the regulator or the ASME. So therefore that it will be difficult for us to use that type of approach to support license application. But well, there's something that will be good for further discussion. Sort of when I look at this, that's probably not. Over.
What if a material is listed in another section of ASME but not approved in section 3? Would that be acceptable?
No, like I said, that Sue also emphasized, we were looking at sort of support near-term deployment. So one of the things that I want to philosophize is that if you can make the process work for the alloy that we call out, and also plus if you can deliver this sort of methodology, predict mod seams, etc., then you should be able to apply to the favorite alloy that you have in other part of the other section of the code. So I don't really see the logic of sort of going to look to work on a different material and then say that, well, my developed methodology can also help you to diffusion bond the alloy that you're very much interested in. So I think that there is a little bit the other way around. So I don't know what is your thoughts, Sue.
Yes, I agree with you. We're looking towards deploying this technology as quickly as possible, so we'd like to focus on the alloys that are already approved.
And also that we know that, as Sue sort of explains, that different alloys like 316L, you can diffusion bond that quite easily, but for some of those high temperature alloys, the process gets to be tough, as we have seen some of the data. So if someone pick an alloy, it's very difficult for us to judge whether you're just lucky to pick an alloy that you can diffusion bond, but then when you bring the process to the alloy that we're interested in, for high temperature applications, we might get back to the same technical issue that we have. So that's the reason why that we want to have the IRP team to prove that you can sort of diffusion bond this type of high temperature alloys and do all the other things that as listed as the goals for this IRP project. Over.
Thank you, Sue, and thank you, Sam. Those are all the questions we have for the IRP-RC1 area.